I already ran this experiment so you do not have to. One discarded microwave pulled from a curbside on trash day. 2 hours of disassembly and rewiring. $0 spent. A fully charged smartphone at the end. I documented every step, every measurement, and every mistake, including the one that nearly ended the project before it produced anything useful. Here is the complete teardown and the build. I want to tell you how I found this, because the path to the solution is part of the solution. 6 weeks ago, I was thinking about the problem that comes up every time the grid fails for more than a few hours. Phone battery dies, power bank eventually dies, and then you are genuinely isolated. I had been reading through old amateur radio literature, specifically the homebrew generator section of the 1968 ARL handbook, and I kept encountering references to salvaged transformer cores as the basis for improvised low-voltage generators. The principle is well established. A transformer core is a precision piece of laminated electrical steel. The magnetron in a microwave is attached to a transformer, the microwave oven transformer, abbreviated MOT, that is one of the most robust and energy-dense transformers available in any household appliance. Engineers who work with high-voltage power supplies have known since the 1970s that the MOT's primary core is ideal for rewinding into a lower voltage, higher current configuration because the steel quality is excellent and the window area is generous. The MOT rewinding community has existed on amateur radio and electronics forums since at least 1995. The specific application to emergency phone charging via manual kinetic energy is what I added to the existing knowledge base. None of the underlying physics belongs to me. Michael Faraday described electromagnetic induction in 1831, establishing that a changing magnetic field through a coil of wire produces an electrical current in that wire. Every generator ever built, from the massive turbines at Hoover Dam to the dynamo on a bicycle wheel, operates on that same principle. The MOT rewinding technique was documented in detail by amateur radio operators and electronics hobbyists in print publications through the 1980s and in online communities through the 1990s and 2000s. What I did was combine an existing technique with a specific emergency application and test it from start to finish with documented results. So let me show you what I found.
The science that makes this possible is transformer core geometry. The MOT has 2 coil sets wound around a laminated steel core. The primary coil, which connects to household current, is wound with many turns of fine wire and steps up the voltage from 120 volts to approximately 100 volts to power the magnetron. The secondary coil, the part that actually drives the magnetron, is wound with just a few turns of very heavy wire. When we bypass the magnetron and remove the secondary winding entirely, we are left with a high-quality laminated steel core with the primary winding still intact. That primary winding now becomes our new secondary. We wind a new primary around the core using turns of wire calculated to produce the voltage and current we need. Think of it like inheriting a high-quality engine block from a discarded car. The original engine configuration is not what you need, but the block itself is precision machined steel that you can rebuild into something entirely different. Here is the part that gets me every time I think about how many of these transformers go into landfills every week. A microwave oven transformer weighs approximately 4 to 6 pounds. Almost all of that weight is high-grade laminated silicon steel, the same material used in precision industrial transformers. When a microwave fails, the magnetron or the capacitor or the control board is almost always the cause. The transformer itself is virtually never the failure point. So when a microwave dies and gets thrown away, a working, high-quality transformer core goes with it. Every curbside trash day produces several of these within a few blocks of wherever you are reading this. Here is what this build costs. $0. That is the number, and I am not rounding down. The microwave came from the trash. The magnet wire for the new primary winding came from a discarded electric motor I had from a previous project. If you do not have salvaged magnet wire, a spool of 20 AWG magnet wire sufficient for this project costs between $4 and $7. The rectifier diodes came from an old circuit board. New 1N4007 diodes cost about $2 for a pack of 100.
The capacitor for output smoothing came from salvage. A new 1000 microfarad electrolytic capacitor costs about $1. If you purchase every component new, this build costs under $10. If you salvage as I did, it costs $0. The magnet wire, diodes, and smoothing capacitor are all linked in the description below and in the first pinned comment with exact specifications, so you can source them before you start. For those of you who want to go further than a single emergency charger and understand how improvised generation sources can be integrated into a complete off-grid power plan, the Energy Revolution system covers that architecture in full. You will see a QR code in the bottom right corner of your screen right now. Point your phone camera at it, and it will take you directly there. It goes deeper into combining multiple generation methods into a working household system than any single video can cover. Now let me walk you through what I actually did, in the order I did it, including the mistake. Safety first, and I mean this without drama. A microwave oven transformer in its original configuration steps voltage up to 100 volts, which is immediately lethal at any appreciable current. Before you touch anything inside a disassembled microwave, the high voltage capacitor in the circuit must be discharged. A microwave capacitor can hold a lethal charge for weeks after the unit is unplugged. To discharge it safely, connect a resistor of approximately 10 to 20 ohms and at least 10 watts across the capacitor terminals using insulated leads, leave it connected for 60 seconds, and verify with a voltmeter that the capacitor reads 0 volts before touching anything else. Do not skip this step. Do not abbreviate it. Do it exactly as described before proceeding. With the capacitor discharged, remove the magnetron, the capacitor, and all associated high-voltage wiring. You do not need any of it, and none of it should be in your workspace once the core is removed. What remains after that removal is the transformer itself, which is now safe to handle as long as it is disconnected from any power source. Here is where I made my mistake, and it cost me about 40 minutes. I attempted to remove the secondary winding, the heavy, few-turn coil wound with very thick wire, by cutting it and trying to unthread it from the core. The secondary is typically potted with a lacquer compound and wound in a way that makes removal difficult without a hacksaw. I spent 40 minutes trying to unthread it before I found the correct method in an old forum thread. Cut through the secondary winding flush with the core on both sides using a hacksaw, then use a chisel and hammer to knock the cut coil sections free from the window. This takes about 4 minutes. The longer method I tried first did not work. The chisel method works cleanly, with the secondary removed. You now have the core and the primary winding. The primary winding stays in place. You will wind your new coil in the empty window space left by the removed secondary. For a generator application producing approximately 5 volts DC output, suitable for USB phone charging, you need to wind a coil that produces about 7 to 8 volts AC before rectification, accounting for the voltage drop across the rectifier diodes. For a hand crank application where the input frequency and voltage are variable, the exact turn count is less critical than in a fixed frequency application. Wind 60 to 80 turns of 20 AWG magnet wire through the core window, keeping the turns tight and even. 60 turns produces lower voltage at lower crank speeds. 80 turns produces usable voltage at a wider range of crank speeds. I used 72 turns in my final working configuration. Here is where most people ruin the winding phase. They wind the new coil loosely, with gaps between turns and layers crossing at odd angles. A loose, uneven winding has higher resistance and lower coupling efficiency than a tight, even one. Think of it like packing books in a box. Stacked neatly, you fit twice as many in the same space. Thrown in at random angles, you waste the available window with air gaps. Wind each turn touching the previous one. Keep each layer flat before starting the next. It takes about 20 minutes done carefully, and the difference in output is measurable. Connect the coil output leads to a bridge rectifier built from 4 1N4007 diodes arranged in the standard full-wave bridge configuration. Connect a 1000 microfarad smoothing capacitor across the DC output. Connect a USB charging module, which you can pull from any discarded USB power adapter or purchase for about $1, across the smoothed DC output. This is your complete charging circuit. Run the output leads to a USB-A port, salvaged from any discarded USB hub or purchased for negligible cost. Connect your phone cable. Rotate the transformer core using a handle attached to the primary shaft. At approximately 60 to 80 rotations per minute, the output voltage reaches the 5-volt threshold needed to initiate charging. My phone registered a valid charging connection and began accepting charge at 70 rotations per minute, measured with a simple tachometer app on a second phone. Feel the transformer core after 5 minutes of cranking under charging load. It should feel cool to the touch. Any warmth in the core indicates eddy current losses that are normal and minor. Significant heat, more than you can comfortably hold your hand against, indicates a winding short or a core lamination problem. Stop, inspect, and identify the issue before continuing. At 10 minutes of steady cranking, my phone had received enough charge for one emergency call and about 40 minutes of standby use. At 30 minutes of cranking with a partner taking turns, the phone was at 22% battery. A full charge from zero would require approximately 2.5 hours of continuous cranking at modest effort. That is real, documented output from a transformer someone left on the curb. This is not really about microwaves. It is about the specific understanding that the tools for independence are already around you in discarded form, built with precision and durability by engineers who intended them to last, thrown away because one component failed. It is about the quiet confidence of knowing that even if every store is closed and every grid is down, there are transformers on the curb and the knowledge to use them. I do not want you to disassemble a microwave this afternoon without doing the capacitor discharge step first. That is the one step where skipping the instruction has consequences that no amount of retrospective knowledge repairs. Do the discharge step, verify 0 volts, then proceed with confidence. If this microwave rebuild changed the way you look at what the trash can offer, please subscribe and like the channel. We are unearthing practical wisdom that the modern world has tried to bury. Charge your future from what others discard. The next treasure of forgotten knowledge will be revealed soon.